few stories. So let me briefly introduce you to my background. So I am a PhD student in biomedical engineering in collaboration with IIT Delhi and AIMS. So AIMS is a technical, not non-technical, like a medical institute, All India Institute of Medical Sciences, and IIT, which is the place where I primarily work, it is Indian Institute of Technology, concerned with military engineering. So since coming from a multidisciplinary background, I hope this will interest to a wide variety of audiences. So coming to a title of the presentation is Fast and Accurate Model to Detect Ictal Response in Active Encephalopathy. So the outline of our presentation is I will be speaking on the definition of epidemiology, the diagnostic method, motivation behind my research work, methodology involved, results and conclusion, and the work in the progress. So first of all, I hope most of you people know what is epilepsy, right? So it is the most, not the most, second most common neurological disorder in the world. Already see more than 65 million people worldwide are affected by it. And just to give you a hint of it, that how much people are affected, these are some of the common people, famous people, those who are affected. Alexander the Great, Leonardo DiCaprio, Napoleon, Newton, and the list goes on. And this is Tony Gray, famous cricketer from this place, England. So, okay, coming to the topic of my research. So a more formal definition of epilepsy is it is derived from it is a chronic neurological disorder which is characterized by recurrent seizures, which is commonly known as fits, which is result of proximally uncontrolled discharge of neurons. So basically this word was actually derived from epilepsy, which means to positive hold. The clinical manifestation range from major motor confusion to lack of awareness. It has a stereotyped radical nature of attacks. So this is the medical definition. Now let's look at the epidemiology, which I already told you, but this actual disease is much more common in developing countries as well because of the lack of resources to diagnose them. Now look at the diagnostic methods involved in this research. So the most common diagnostic method, which is the primary first step of diagnosis, epilepsy, is that taking the history from the patient or the caregiver, whether the epileptic event has occurred in the past or not. And also taking physical neurophysiological tests and exams as well. Clinical lab investigations, which can range from blood tests, liver, kidney, etc., etc. But till date, the most commonly used method for diagnosing epilepsy is EEG, because these are the electrical discharge thing, right? And if you do an EEG for an allotted hour of time and also recording a video simultaneously, it is called video EEG. So this is the area which I work on, and the presentation is on this topic. So first of all, what do you mean by reference program? So EEG is a general way. It's nothing but the electrical activities of the brain. But this which was developed by Hans Berger in 1920. But this can be very useful in a way to assess the cognitive performance of the brain as well as diagnosis of various types of disorders. So basically, EEG can be characterized into different types of waveforms, which can be divided into delta, eta, alpha, beta, gamma. So each waveform basically lists out different types of clinical manifestation over time. So the delta waveform, which ranges from 0 to 3, on some of the books you will find 0 to 4, it ranges between deep sleep, infancy. Theta, sleep, childhood idling, so and so on. Alpha waveform, it ranges between 8 to 13 Hz, which is one of the most commonly studied waveforms in each domain. It is related for awake, relaxed, eye closed. So similarly, there are different forms of different waveforms going still gamma wave. So first of all, what is the motivation behind my research? So let's look at it. So EEG, out of all the biomedical engineering signals available, it is the highly non-stationary signals available to date. I will provide you why. So it is having a large data set, and if I just tell you, I'll just show you these two EEG signals which were acquired from some lab, and I ask you which one of these is an epilepsy signal. Can anybody from the audience tell? Just a quick guess. No, right? So if the audience answers, so the most common answer is the second one is epilepsy signal, the first one is a normal signal. So, but the answer is no. So both of them are actually normal. So the reason why is that when anybody is having some seizure attacks, it's just too noisy or the motion activity is such high that anybody is, the clarity of the waveform is very less. That means the SNR ratio is very low in single person domain. So yes, and also epilepsy is very heterogeneous in nature. That means the seizure attacks might vary from a person to person and within a person as well. That also means the epileptic seizure patterns might vary from person to person and within a person as well. So as you can just imagine, since it's such an heterogeneous disease, there is just so many types of ictal patterns available, it is just very difficult for any neurophysiologist or any neuroclinician to analyze it by visual inspection. I mean, if the inspection needs to be very fast enough, you can just imagine an EEG which is being acquired for ranging from 20 minutes to 6 hours or 8 hours is being acquired visually. Obviously, it will have some kind of manual errors as well, and it will take a hell lot of time as well. So yes, this is very problematic. So the most basic question is, can we actually automate this process? The answer is obviously yes. Many researchers have tried it in the past. Let's see what is our intervention. So the methodology involved was this. Most of the people have used University of Bonn database. So it is kind of a benchmark database in this domain for developing expert systems which are being used by people working in computer science language, people like me, to test their algorithms. But this is not enough. Okay, why? Because it is not being tested into the practical domain. So we also tested our system in clinical settings in India. So, and India is a good place to work. Why? Because you have the actual errors which you get a lot more. So this is the basic methodology involved. So ideally the signal should be like this, but it doesn't come. Why? Because due to many other factors as well. A person will within a little bit of movements produce signal like this. Okay, but it has the hidden waveforms. That is the hidden waveforms as well, right? Hidden in the signal. These waveforms can be characterized to certain stages. Person might not be having seizures in normal patient, or a pre-ictal stages, which is just the stage preceding the ictal stages, and a post-ictal stage, which is called there is also a stage called post-ictal stage as well. But for the simplicity, we are just considering here two stages, that is the ictal stages and the non-ictal stages. So there are various time frequency domain analysis techniques available, but there is a lot of lacunae. So we developed our own feature set, which is using empirical mode decomposition. Quite simply, what it does is that it decomposes the original time series of signals into a set of many time series of signals, and it provides you an interesting mode function of it, which can be used to plot the phase trajectory. Now the phase trajectory has been used in control theory quite a lot to discuss how the non-linearity of the system is working on. So non-linearity is the key word over here. So epilepsy, EEG, all these things are non-linear in nature, and this is the perfect thing to characterize. And here we calculate the Euclidean distances. Euclidean distance is nothing but the distance between the points. Okay, and then we calculate the standard deviation to form the feature sets. This is being used to train. These are the feature sets. So as you can see, these are the feature sets of non-ictal stages. These are the feature sets of ictal stages. As you can see from the feature sets itself, that the non-ictal stages are following some kind of epileptic trajectory, which is very uniform in nature, whereas the ictal patterns are following the epileptic ellipsoidal kind of trajectory, which is not uniform in nature. Still you can see. Okay, and if you can actually calculate these variances, it will be very helpful in guidance. Okay, so we just put these things, these feature sets into a machine learning classifier. From those of you from a machine learning background, I use a probabilistic neural network. Okay, it's just nothing but a very fast feed-forward neural network classifier, which is also being statistically validated. Now, quite simply, we talk about classification accuracy. Basically, what it means is that how much is your expert system is providing the correct results, which are, if you compare with the original ones. So it is providing us 98.12% of results. And another important factor which we looked upon is the sensitivity and the specificity. Simply defining sensitivity, it means the ability of the expert expert system to classify the disease patterns. And vice versa, the specificity denotes the ability of the expert system to classify non-severe patterns. And most of the previous literatures, you will find that they have a large gap between them. Some might have a sensitivity of 96 and specificity of 86. So you need to make this more coherent in nature, which you've already got. And we also characterize the computation time to characterize it, which is quite nice. So the conclusion is we are getting more than 97% of accuracy, and it demonstrated high outcome analytics. Okay, so this is something under progress. But why I call this under progress is that what about the practicality of the system? Is artificial intelligence good enough to diagnose a certain persons suffering from epilepsy or not? So the answer is actually no. So these are algorithms which are good for validation, but also it has to be applied in practical domain. So this is one of the recent patent we filed, and I show you the picture of this Nataraj. Why? Because Nataraj has just put a step on apasmara. Apasmara, according to the Indian methodology, used to suffer from epilepsy. So as a perfect example, Nataraj has stepped on apasmara and the person is free from epilepsy. So this is a brief video how we can apply the system in practical domain. We just forward the working. So how the tool works is that you just directly need to load the signal. That's it. Previously, the tools how they used to work was that they were mainly based upon the template matching algorithms, which actually means is that it depends upon the user to actually initialize the patterns, and based upon the initialization provided by the user, it will actually automate the process, which is actually not automation in a way. So it is directly completely automated. It will directly show you the pictorial patterns where it is coming from, and there are various sorts of console options which I have provided. Not only provides you the range of pictorial waveform where it is coming from, and it also shows you, it localizes over the scalp as well, over the cortex as well, where the items might be coming from, which is also on the right. So this data was actually taken from an occipital lobe epilepsy patient. And as you can see, occipital lobe epilepsy means is that a person might be having epileptic seizures on a particular location, that is occipital lobe in this case, and rest of the patterns might be non-epileptic. So the blue patterns are non-epileptic. The red pattern, which should appear in the movement, are the epileptic ones. So this was recently patented. These are the epileptic patterns, and has correctly classified into the O2 region. And it provides you different consoles. You can change the view of this as well, which is some relative position, inferior, axial, different positions. Okay, so I will just do it. So the future scope of the research. So till now we have been, good enough to classify the actual patterns and also apply those things for the clinical domain. But what about predicting the seizure patterns? Predicting, what I mean by prediction is that if we could actually detect the pictorial patterns, we could actually predict where the seizure is coming from. For example, a person driving, an epilepsy patient might be driving, and he gets a trigger that you will be having these kind of fits in a movement. You can just park your car outside and wait for the assistance. Okay, so this could be very helpful in nature. So this is one of the data sets which we recently developed. Most of the data sets available online are either based on intracranial EEG, which is much more common in European countries or US, but absolutely not common in Asian countries. Okay, and as you can just imagine, intracranial EEG, what it means is that you just remove the scalp of the patient, obviously you put it back as well, but while you remove it, you acquire the EEG signals, and it actually provides you a very good information about the localized position of the epileptic seizures Why? Because you are directly poking on to the area where the seizures might be coming from. Okay, so scalp EEG processing is much more difficult, which we just did. So yeah, this might be based on Windows-based classifier as well, which we have already used. Okay, and it will do auto-sample analysis. What do I mean by auto-sample analysis is that I might be using to train a expert system. I might be using patient from A hospital and might be testing onto the B hospital. So that has also not been done previously. These are some of the references. And I would just like to end my presentation with a short note by Hans Erickson, not me. Keep on the lookout of novel ideas that others have used successfully. Your idea has to be original, only its adaptations according to your working, which perfectly fits with my research. Thank you.